Welcome to CivilizationX. Science depends on iteration. Most labs still stop when humans go home. But in one real materials lab, a mobile robot kept going for 8 days, ran 688 experiments, and chose new trials from its own results. At 6:40 on a Wednesday morning, a second-year PhD student unlocks a quiet lab expecting to check yesterday's samples before her committee meeting. Instead, the system has already run overnight, ranked new material candidates, and left her 3 options on screen: confirm, override, or let it continue. This is not automated pipetting. It is a closed experimental loop. In 2023, a Nature AI chemist system used large language models plus robotic hardware through structured control layers to plan and execute chemical synthesis with minimal human intervention. At Argonne, a lab linked planning, synthesis, and characterization into autonomous materials discovery. The real question is not whether machines can run experiments faster. It is whether a lab can choose its next experiment well enough to change what science is. A normal lab cycle is serial. Define a target, prepare samples, run instruments, analyze data, then decide what to try next. Autonomous labs close that loop. Humans set the objective function: yield, stability, activity, bandgap, binding, whatever matters physically. Software proposes candidates from prior data and constraints. Robots mix, heat, deposit, pipette, or measure. Analysis scores the outcome. That score becomes the input for the next choice. And the loop repeats until a stopping rule is met. That distinction matters because modern search spaces are combinatorial. In catalysts, batteries, perovskites, thin films, and protein engineering, the possibilities scale into millions or billions. Sequential human planning becomes the bottleneck. Closed-loop materials platforms now choose the next formulation algorithmically instead of following fixed design schedules, cutting physical trials versus exhaustive search. The Liverpool robot proved the concept in motion. DOE programs scaled it into infrastructure. Then biology changed. In 2022, AlphaFold released predicted structures for more than 200 million proteins, described as covering virtually every protein known to science. Structural biology no longer always begins by waiting months or years to solve one structure. It now often begins by filtering a near-total catalog first, more like search than excavation. As Edith Hurd put it, this is like having a search engine for structural biology. The same inversion is hitting chemistry and materials. Not can we test at all, but which candidate deserves the next test. So, what has the lab machine achieved? It compresses decision latency. The student returns not as a pair of hands, but as the designer of goals and the auditor of trust. But speed cuts both ways. If calibration drifts, metadata are weak, or contamination slips in, a closed loop can optimize nonsense hundreds of times faster. Large models can also produce chemically plausible but invalid plans, which is why real AI chemist systems need hard execution layers and safety constraints. Over the next decade, the frontier is not robotic motion. It is reliable autonomy across expensive instruments, standardized metadata, and reproducible reasoning paths. Smaller universities, lower resource labs, and early career researchers could benefit last, while losing bench intuition first, if access stays capital-heavy and proprietary. By the end of that week, the system has surfaced a promising candidate faster than any normal lab schedule could. She approves it only after tracing why it was chosen. That is the unresolved engineering problem now. Can another lab reproduce not just the result, but the machine's reasoning through failures, drift, and hidden software layers? The constraint is real. The data exists. Whether the systems built around it can act on it at scale, that is the next engineering problem.